Okay, catalytic hydrogenation using metals. Not much you need to know with this. And actually, the platinum, nickel, and I think rhodium don't really need to, I really don't think those are going to pop up. There's stuff in your book about them, but they're really going to be all behave about the same. And they usually require like really extreme temperatures and pressures even to get some product. So you can kind of group all of them together. Some of them have used for certain functional groups and some of them not, but they're not selected because all four of them will react with like carbon-carbon double bonds, but then you can also use them for other things and so on. The main one we'll be using is palladium. Most often not, but again, if you see any kind of metal on there, it's going to act pretty much the same way. The important thing to know with these metal catalysts, so here we have palladium on carbon, we have H2, and when I don't have anything else written here, I just have one equivalent of H2, assume that. I'm turning an alkene into an alkane. I'm adding two hydrogens, one on each side of my double bond, and I'm reducing my alkene to an alkane. Here I have the, here I have the Z conformation, but that's more important than the next ones. Here I have an alkyne, okay? They are, metal catalysts are able to reduce an alkyne all the way down to an alkane, but we need two steps, and that's why we have at least two equivalents of H2, or if we had excess H2, it'd be the same. Pretty much it. And then we have an alkyne down here, and we have the addition of what's called a poison catalyst, Lindlar's catalyst. It's poisoned because it doesn't really do the full reduction mechanism all the way. Notice it stops at the alkene. It doesn't continue and keep going to the alkane. So it stops at the alkene, and not only that, it stops at the cis or the Z isomer as well. So it's poisoned because it doesn't go all the way down to reduce. Even when I have as much H2 as I want, if I put Lindlar's catalyst there, it can only go down to an alkene, and it can only be in the Z isomer. These are important for synthesis or write the product. Not much you need to know with that, other than maybe just a little bit of stereochemistry and a little bit of stereoselectivity with it. So here I have my metal catalyst. It can be zinc, palladium, platinum, rhodium, rainy nickel, anything, okay? And they're all going to work the same in that they're going to reduce our molecule. They're going to add two hydrogens onto a double bond, and some of them will again react with other functional groups. The important thing to know though is that when I'm adding my hydrogens on there, I'm doing so at the same time, okay? So both of my hydrogens will either be, my new hydrogens that is, will either be both wedges. In this case it's symmetrical, so it'll be the same, but you get the point. So adding on the same side, either the front or they can add on the back, and they both be wedges. So we have our alkene, and those hydrogens are being added at the same time. So they have to choose either adding on the front or they have to add on the back. So they'll both be dashes or they'll both be wedges. I think there is an example in the whiteboard that shows, I believe it should be something like, we'll say it's a wedge, like a methyl group there, okay? And it is treated with, say, H2, palladium on carbon, okay? We should expect our alkene to be reduced to an alkane, so that'll go away. So that's gone away. And if we keep our methyl group, we'll say our hydrogen is added on the back to begin with. And that would make sense. The methyl group's already sticking out. So our hydrogens are going to add on the back side. Methyl group would be on the front, and our hydrogens will be going back. Okay? Now, what if our hydrogens added on the front? If they added on the front side, our methyl group would move back. Our hydrogens would both be wedges, and they have to be on the same side. They're being added at the same time. Okay? So notice that we get, well, in this case, we get, would be the same molecule, because we can flip that and it'd be the same. Maybe in the whiteboard there was an addition of, there was most likely, I think, yeah, there was like a methyl group over here, okay? So in our case, we made the same molecule, but if we had something like a methyl group over here the whole time, and didn't react with our metal catalyst at all, now, notice, we've made a pair of diastereomers, okay? So that has to do with the stereo, can't even think of the words right now, but it's okay. So just know that they're added on the same side. Stereochemistry on those are going to be either diastereomers or they could be the same. So there might be a question about that on your assessment. The last thing with this I'll talk about is stereoselectivity. Basically, you have a large metal catalyst and you have these two little hydrogen atoms that are going to be added on. So you have that large metal catalyst. It's going to want to first add on to the less substituted spot, the one that's less sterically hindered. So in this case, I have an alkene here with two substituents on it, and an alkene here, terminal alkene with only one. So if I only have one equivalent of H2 and something like palladium, I would expect this alkene to be reduced first, and my hydrogens to be added here first. If I had two equivalents, I would get rid of this one, but just as a general rule, these metal catalysts are going to favor the less sterically hindered spot. Okay, that's going to be it right now for catalytic hydrogenation using metal catalysts. And next we're going to get into Wolff-Kishner, Clemenson, and Rainey-Nickel. They're a little confusing, but I think if we stick with the examples Dr. Andrews uses, I think we'll be okay with that. So that'll be the next video.